Spring potential energy. Work done by an applied force in stretching or compressing a spring can be recovered by removing the applied force. So, like gravity, the spring force is conservative. This means a potential energy function can be found and used in the work energy theorem. The first image shows the spring in its equilibrium position, where the spring is neither compressed nor stretched. Pushing a block against the spring, as in the second one, compresses it at distance x, where x represents a displacement from the equilibrium position, which will always be taken to be at x equal to 0. Experimentally, it turns out that doubling a given displacement requires double the force, while tripling it takes triple the force. This means force exerted by the spring Fs must be proportional to the displacement x, or Fs equals minus k times x, where k is a constant of proportionality, the spring constant, carrying units of newtons per meter. The force Fs is often called a restoring force because the spring always exerts a force in a direction opposite the displacement of its end, tending to restore whatever is attached to the spring to its original position. As in the case of gravitation, a potential energy called the elastic potential energy can be associated with the spring force. We determine the work done by the spring when compressed by an applied force from equilibrium to a displacement x, as in this one. The spring force points in the direction opposite the motion, so we expect the work to be negative. To find the spring force, we use the average force F, determined by this equation. Therefore, the work done by the spring force is determined by this equation. In general, when the spring is stretched or compressed from xi to xf, the work done by the spring is determined by this equation. The work done by the spring can be included in the work energy theorem. Assume its equation includes the work done by the springs on left-hand side. It then would read as follows. Where PEG is the gravitational potential energy, we now define the elastic potential energy associated with the spring force, PES, by this equation. Inserting this expression to the previous equation and rearranging gives the new form of the work energy theorem, including both gravitational and elastic potential energy, with this equation, where W and C is the work done by non-conservative forces, chi E is kinetic energy, PEG is gravitational potential energy, and PES is the elastic potential energy. This figure shows how the stored elastic potential energy can be recovered when the block is released, the spring snaps back to its original length, and the stored elastic potential energy is converted to kinetic energy of the block. The elastic potential energy stored in the spring is 0 when the spring is in its equilibrium position, x equal to 0. Potential energy is also stored in the spring when it is stretched. Finally, because PES is proportional to the square of the displacement, the potential energy is always positive when the spring is not in the equilibrium position. In the absence of non-conservative forces, W and C is equal to 0, so the left-hand side of the equation of the work energy theorem is 0, and an extended form of the conservation of mechanical energy results in the following equation.